Hi class, today we're going to look at lesson 2 of our circuits unit, and this lesson has to do with a very important law that allows us to analyze circuits and learn about um, the relationship between volts, current, and resistance. This is known as the Ohm's law. So let's go ahead and take a look at resistance and Ohm's law. So to help understand the ideas involved in electric circuits, I'm going to make an analogy, and I'm actually going to use the bottom of the page, actually on page 10. Let's go ahead and write some notes on the bottom of page 10 here. So we looked at circuits yesterday in our previous lesson as having three parts. So the parts are you have to have a source, a path, and a load. So in an electric circuit, I'm going to look at an analogy here. So you have an electric circuit, and I'm going to compare this with water in a pipe. So I'm going to make a water and pipe analogy here. And I'm actually also going to make an analogy here with your heart, your circulatory system. So those of you who have taken biology, we could compare that with the heart and the blood vessels and the blood itself. That would be the parts of the circulatory system. So let's make our chart here. So in a circuit, you have a source. This will be the source of the EMF, the battery, or the voltage. So this is the source. And in a water pipe, now imagine you are on the second floor, like our physics lab, for example. How do you get the water from the well or from the basement all the way to the second floor or even higher? Well, you have to have a pump. So the source of the flow in a water pipe is a pump, a water pump. In a circulatory system, what pumps the blood is the heart. So the three parts of a circuit, you have the source, and then you have the path. In this case, that would be the wire in an electric circuit. In water that is running in the pipe, the path would be the pipes itself. And the circulatory system, the path that carries the most important thing that is needed by our cell, the blood, is carried within the blood vessels. And the third part of a circuit is the load. So in water in a pipe, okay, so in a circuit, the load is the electronic device. So that would be the device that you're trying to power up, whether it's a light bulb or it's your iPhone or your computer. That would be the load. Water in the pipe, this would be the load would be the faucet. So this is what controls the flow. So I'm going to just write down a little bit more information here. So the source, the voltage, this would be the push. So this pushes the current in a circuit. In a water pipe, of course, it pushes the water, and in the circulatory system, it pushes the blood. The path, this is what carries the current. So the wire is the path in a circuit. The pipes would be the path in a water pipe, and in the circulatory system, it would be your blood vessels. And then, of course, the load is what resists the current. So it this is the device that actually slows down the flow of current, and that would be the device that you're trying to power up. This is the faucet that controls the water in the pipe. And in the circulatory system, it would be your cells that will be using that blood. So I'd like to use that analogy to compare the circuit with water running in a pipe and our circulatory system. So that is the big idea about the circuit. So in electrical circuit, we have we have the resistance. So the electric resistance can be defined in terms of two quantities that are already discussed: the electrical potential difference, or the voltage, and the electrical current. So the resistance is defined as the ratio of the voltage, or the V, applied across the conductor to the current that is running within that conductor through the material itself. The ratio then is the voltage over current. So V over I, and this is the resistance. So this ratio here will be equivalent to the amount of resistance, or the slowing down of the electron, or the current, actually, more importantly, as it flows through the conductor. So this is Ohm's law. You can also see Ohm's law in the form of V equals IR. This is the formula for Ohm's law. And this was first described by a person by the name of Georg Simon Ohm in the 18th century, and he discovered the relationship between voltage, current, and resistance. So this Ohm's law is very important in our study of circuit, and later on in our circuit analysis of the relationship between the R, the V, and the I. So this ratio is always going to remain constant, which means that the resistance is going to be a constant resistance. Now, I'm not saying that the number for the R is always going to be the same in terms of a number. So it's not a constant like 9.8 meters per second squared for the acceleration of gravity. This means, though, that if you change the V, it will also change the I proportionately, so that the resistance is going to be the same. And a device that follows this relationship is known as an ohmic device. So I'm just going to go over this next section here. So Ohm's law states that the ratio V over I is a constant, where V is the voltage applied across a piece of material, such as a wire. So this is, of course, a conductor. Well, what is the difference between a conductor and an insulator? Conductor allows electrons, and therefore current, to flow through and out of that material. So an example would be a metal, like copper, for example. It would be a very good conductor. If you apply some electrons on one end, the electrons will freely flow through that material and out of that material. Whereas an insulator, the electrons do not allow are not allowed to flow through. So they do move. So when you say static electricity, that is actually not true to say that the electrons or the current are static. It just means that insulator does not allow the electrons to flow through and out of the materials easily. So the electrons are they kind of stuck, the electrons and the current, they are stuck within the material, and they don't really freely flow. So If you take a look at the units now, so the unit for V is volts and the unit for I is amperes from Andre Ampere. So the unit for resistance, V over A, is the volts over amperes is actually ohms. This is the symbol for the unit that we give resistance. So these are actually all named after people who first described that idea. So volt from volta and Andre Ampere for amps, and of course the German physicist Georg Simon Ohm. So to further discuss what an ohmic device is, so if a device, it's gonna, a device, an electrical device that follows this idea of V over I being a constant R. So if the resistance remains constant, this is known as an ohmic device. And if you were to look at the chart in an ohmic device, so if you were to graph the volts versus the current, it will be a linear relationship. So this shows you that V is proportional to I, and this is what happens in an ohmic device. In a non-ohmic device, this law is not followed. So non-ohmic device, then the resistance will vary. So this is an example of a non-ohmic device would be a thermostat, for example, or a thermistor, a resistor that depends on temperature or the difference in temperature or heat energy. So in a thermostat, for example, you have a bimetallic strip that detects the change in temperature depending on what you set it as. So let's say you want your house to be at 20 degrees Celsius, and you open the window or the door and the hot air goes out of the window or the door and the house cools down to say 18, then the bimetallic strip then will react to this change in temperature, and it will bend, and it will then trigger a switch that will turn on your furnace to heat up the room again to whatever temperature you set it as. So this is an example of a non-ohmic device. An example of these ohmic device would be like a copper wire, a resistor, or a heating element. So where the resistance is always going to be constant because the volts and the current will increase proportionately because it is a proportional, direct proportional relationship. So that is Ohm's law. Now let's take a look at circuit diagrams and Ohm's law. Again, it tells you here, a resistor is an electrical device that offers resistance to the flow of electric charge. So that the name kind of tells you that a resistor is an electrical device that offers resistance to the flow of electric charges. Doesn't that remind you of friction? So friction basically slows down motion. This offers resistance to the flow of electric charges. So resistors can have a wide range of resistance values. They can range from a very small number to millions of ohms. And it depends on what they're trying to do. So let's take a look at this first example. A flashlight is a simple example of an electric circuit. If you have two 1.5 volt battery and you have two of those, so the volts will then be 1.5 times 2, which is 3 volts, placed in a flashlight. The total voltage is equivalent to 3, okay? Typical current for such a circuit could be 0.4 amps. So if you look at those batteries that you usually buy at the store, you have those triple A or A or C and D. Those are all actually the same volts. They're all 1.5 volts of potential difference, even though they are different sizes. Ironically, you probably recall that you've seen those 9-volt batteries, those rectangular prism size ones. Compare that to a 6-volt lantern battery. 6-volt is actually a lot larger. It's about the size of your mug compared to a 9-volt battery. So it's not the size that determines the volts. The volt is basically the kick that pushes the electrons and the current out of that battery. Okay, so the current here in this question is 0.4 amps. A possible diagram for such a simple circuit is as shown below. Okay, so let's start with when you're creating a diagram for a circuit, you start with the power source. That makes it easier. So you have 2 of these batteries. So I'm going to connect the positive and the negative. So the negative is the short end of the terminal and the positive is the longer end. And then you have, so that's the source. Now you have your path and then you have your light. So here's a very simple schematic or an electrical circuit diagram of this flashlight. So you have your 3 parts, source, path, and your load. So there's a very simple circuit diagram. If we were to calculate the variable that's missing here, even though it didn't tell us, we could actually now use Ohm's law to calculate the resistance. So V equals IR. So R is V over I. And so you have 3.0 volts divided by 0.4 amps. And what do we have? Get your calculator ready. And you have 7.5 ohms of resistance. It actually asks you to do it down here. So that is the value of the resistance in this very simple flashlight. So here's an application of the Ohm's law. So that is the relationship between resistance, volts, and current in the form of Ohm's law. So Ohm's law is a big idea when you look at electrical circuit. So V equals IR, or R equals V over I. This is Ohm's law. Now what about this other term called resistivity? So resistivity is not the same as resistance. So we know that resistance is the slowing down, or the resistance to the flow of current, how much the material resists the flow of current. What is resistivity? Okay, let's define these words. So resistance opposes the flow of free electrons. So it opposes free flow of electrons. And resistivity is actually a property of material. So you know how if you look at something and then you wonder, is this going to float in water or is it going to sink? So we know that as the ratio of mass and volume of that object. We call it density. So just like density, resistivity is a property of the material to resist the flow of electrons within that particular dimension. So it is a property of the material which defines the resistance of the material with specific dimension. So it's very much like density. And resistivity can be affected by temperature. So an example of a superconductor is if you take a copper and you just super cool it, and there you go, you have just turned that into a superconductor. So it's as easy as that. Uh, so resistivity can be affected by the temperature of the material. I'm just going to write more information here about resistance and resistivity. So the resistance of a conductor depends on the length L, the area, surface area, and temperature. Resistivity actually has this symbol, whereas resistance is just the letter R. And this is from the Greek letter R, rho, for resistivity. So resistivity depends only on temperature. So it's not affected by length or area. It depends only on temperature. So looking at the relationship, resistance is proportional directly to the length. So basically that means that as the length increases, the resistance will also increase. So this is one reason why it is not a good idea to be using an extension cord to power high voltage and high power appliances like your fridge, your oven, your washer and dryer, your dishwasher, and big appliances at home. You should be plugging them in directly into the wall, and they should have their own circuit that's not going to trip the fuse or the circuit breaker of the other appliances. Because the longer the wire that you use, the more resistance you're going to get. So you try to minimize that resistance so that you don't burn that wire and cause fire, because resistance is directly proportional to the length. Resistance is inversely proportional to the area. So as the area increases, resistivity decreases, and vice versa. So this is an inverse relationship. So for example, if you have a wire and it is smaller, it's narrower, and it's not as thick, the resistance would actually be higher. So that is why, again, if you're using high power, high voltage appliances, you want to make sure that you're using a thicker diameter, thicker surface, thicker area, cross-sectional area of that wire. So here's your wire, for example. This is the area that you're looking at. So you want to make sure that the, the wire is thick to accommodate the high power, high voltage appliance that you're powering up, because the resistance is inversely proportional of the area. What about resistance and resistivity? Resistance is directly proportional to resistivity. This makes sense because if you are looking at, for example, copper would be able to move those free electrons freely much faster than if you were, say, using iron or brass. So the ability of copper to resist the flow of electron is low, so therefore the resistance would also be low. And resistance, I'm going to just add here, is proportional to temperature. And that would be the same thing with resistivity. So putting this all together, putting all these relationships together that they discovered these relationships in a lab. Resistance is equal to rho L over A. And that tells you again, resistance proportional to resistivity, resistance directly proportional to length, and resistance inversely proportional to the area. So let's look at the units. So the unit for length is meters. Okay. Unit for area is meters squared. And the unit for resistance we know is ohm. So what is the unit for rho or resistivity? Well, just like with anything, if you want to find the unit of a variable, you just isolate it. So isolating this rho, then you get R A over L. So the unit for R is rho, the area is meters squared, and the length is meters. So canceling one of the meters here, resistivity has a unit of ohm meter. The unit for resistivity is ohm meter. That actually sounds like a meter that measures the resistance of the circuit, ohm meter. So here's a chart on your page 13 that shows you the resistivity and the temperature coefficient of some materials. And as you can see, let's look at copper. So copper, the value of resistivity for copper is 1.68 times 10 to the negative 8 ohm meter. And what is lower than copper is actually silver. So that tells you that because silver has a lower resistivity, silver is actually a better conductor than copper. So why do we use copper inside the wires and electrical device, but why not silver? Well, it's all about the abundance in the earth. So copper, because it's more abundant in earth, we use it because it's more abundant, it's cheaper. But now we actually don't make pennies made of copper because it is becoming depleted. So as we get more reliant and dependent on technology and electronic device, we are needing more copper to use as the path of our circuits. So we don't bother with using copper now to make pennies. It's actually more expensive to make a penny. It costs more than a penny to make a penny. So silver, we don't use it because it's more expensive than copper. And gold is actually not as good as copper. So we don't want to use gold as well. It's too soft. So notice that all of the conductors have small resistivities. Insulators have large resistivity. So rubber, for example, is 10 to the 13 to 10 to the 15. So that's a pretty high resistivity. And so rubber is a good insulator. Same with glass. The semiconductors have intermediate resistivity values. So we talked about density. We compared density with resistivity. Resistance depends on the resistivity of the material and the geometry of the material. So the dimensions of it, the cross-sectional area and the length. So for example, you can have two copper wires. So two copper wires will always have the same resistivity. For copper wire, the resistivity is this. So you can have a very long copper wire or a very short copper wire. The resistivity is going to be the same, but the resistance is going to be different because, again, of the relationship between resistance and length, resistance and rho, and resistance and area. But resistivity is a constant property of every material. It's not going to change. The only thing that changes resistivity, I'm going to write this down again. Resistivity depends only on temperature. So if you heat it up, what do you think would happen if you heat up the wire? So you take a wire. So let's say I have this wire. So here's my copper wire, and I heat it up. So I increase the temperature. Now, you might be familiar with the kinetic molecular theory of atoms and molecules. Of course, everything is made up of atoms and molecules, right? So let's say I've got these things, and because we're looking at resistance, which has to do with the flow of electrons, which is called charge, which will then create a current. I'm going to just look at electrons. So you have these electrons because things are made up of atoms, which are made up of subatomic particles, protons, neutrons, and electrons. But when we talk about current, we only concern ourselves with the electrons because it's the flow of electrons that create the current flow. So these electrons are just happily sitting here. Now, they are never really sitting. They're always jiggling. They're always running around. They are never still because particles are always moving. So these electrons are just doing their business, and then somebody turns up the temperature of this copper. So someone heats it up. So now you have a warm piece of wire. What do you think these electrons are going to do? Well, they're going to run around even faster. So when you increase the temperature, these electrons are going to collide with each other, and they're going to so these electrons of the material itself, and now you're trying to get electron to flow through it, which is the flow of current. This current then is going to have a harder time going through it, through this material, because the electrons of the pipe itself, of the wire, they're now running around faster and in random direction. So it's going to offer more resistance. So the warmer or the higher the temperature, the more resistance that material is going to have, because the resistivity is going to increase. And of course, if you increase the resistivity, because temperature affects resistivity of the material, is going to increase the resistance as well. So if you want to make the resistance lower, you want to make the resistivity lower, okay, without changing the length and the area. So what do? You can lower the temperature. By lowering the temperature of the material, you're going to lower the resistivity and therefore lower the resistance. So this is one way you can make a superconductor. When you make something super cooled, you can actually levitate that. You can make it into a superconductor. An example of a superconductor that is being used is the maglev, or the magnetic levitating train. They're not super cooling it, but it is a superconductor that actually that repels the magnet when it's turned on, and the train actually floats. So it's a device with very, very low resistance, and it's a superconductor. Now let's take a look at resistance and power. So in the previous lesson, we reviewed the idea that when electrons pass through a potential difference or voltage, as they do in a wire that is part of an electric circuit, the gain in energy is given by the change in potential energy is given by charge times the volt, or the change in potential energy. We also learned that the amount of electric current passing through a circuit can be defined by current is equal to charge over the change in time. So from previous work, power can be defined as power is equal to QV over change in time. So looking at this, Q over delta T, power, Q over delta T is current. So power is current times volts. So this is another equation that we can now use to solve for electrical power. So electrical power is current times voltage or potential difference. And the unit, what is the unit for power? What is the unit for power? You're thinking about it? I just told you what is the unit for power. So the unit for power is watts, or W. And this was named after George Watts. So he was working with steam engines. I might post a little video about a brief history of all these terms that we're looking at. The coulombs, coulombs, ampere, volta, um, watts, all named after people. So many devices become hot when provided with sufficient power. Such devices might be toaster, iron space heater, heating elements on electric stove, incandescent light bulb. In cases such as these, it is possible to obtain two additional equivalent expressions for the power. So from Ohm's law, V equals IR, or P equals IV. So if I were to now use the formula that we just derived above, P equals IV, because we know that V equals IR, so because V equals IR and V is right here, I can substitute the V into, we still have the I here, so V is now IR. So power is also I squared R. That is another way to solve for power. But we also know that R is V over I. That's actually the better expression for Ohm's law. It shows the proportionality statements here and the ratio of the volts in the current. So if I were to now substitute the R here, then I can go and leave the I squared. Again, I squared, but the R is V over I. That takes away the I and we're back to IV. But now if I look at I is equal to V over R, I'm now going to eliminate one of the I. So from P equals IV, and I'm going to take the I and put the V over R. So I is V over R, and the V is still here. And then you have V squared over R. So we've just derived different ways to solve for power. So P equals IV, but P is also I squared R, and P is also V squared over R. So we've just used the Ohm's law to derive different ways that we can solve for power. And that is the end of lesson 2. So now we have these exercise questions at the end of lesson 2. So please try them on your own. Take a picture, email them to me, and I will give you some marks for it. Boost your marks and email it.